Hello and welcome to another exciting Breakfast with Unity. I'm your host, Max Moreau, and today we're going to be mathing some stuff. So this morning I didn't have time to look at this problem after after yesterday. And so this morning was the first time I took a look at it, and I really should have taken a look at it earlier because it was a little bit more complex than I was expecting. So let me explain why real quick. Actually, first let's open the project and see what we got. That's the wrong Unity. That's 5.0. We're not doing that right now. So, and you can see I've got some notes there and stuff. So we were doing the target lead position thing, and we ran into this problem where if the target is moving away or in front of or towards us, the way we were doing the calculation was we were assuming. Here, I'll show you the original equation that we have here. Ignore this stuff. Just ignore that for now. But I want that there so I can talk about it. So all we were doing is we were getting the distance to the target and then figuring out the time to the target based on that distance and then going to that. The problem is we don't want the distance to the target. We want the distance to the eventual position of the target. Now, the problem with this is we have this circular logic problem. And so I just quickly sketch this out here to show the problem that we have. So we have the final position, which is the target position plus the target velocity times time to target. We have the distance to the target, which is our position minus the final position dot magnitude. And the time to target is equal to the distance to target divided by the projectile velocity. This is all fine, except for there's one problem. Time to target is used in this equation. And so we don't know time to target yet because we can't figure out time to target until we have figured out the distance to the target, and we can't figure out the distance to the target until we have the final position. So yes, this is not as easy as it first looked. So I ended up looking for solutions online, and you can see that this is what it looks like when I'm doing research. So I found the solutions, and I found a okay solution and I found a great solution, but I did not find a good. I found an okay example of the okay solution as to why it works, but I did not find a good example as to why the good solution works. I am working on that. I actually want to give you the proper proof for this. Now, the reason for this is, so this is the okay solution, and what this is basically, it says, just repeat this operation multiple times. Because basically you get an approximation each time, and each time iteration you get a closer approximation. There's diminishing return on this, so there's a certain number of approximations where it doesn't really matter anymore. In particular, it works better if your projectile is moving considerably faster than your target, which is probably going to be the case in most cases. But it is not going to give you the exact answer, and it is possible to get the exact answer. So I'm not going to use it. So, but that's what this guy said on Unity Answers. So I found two examples, actually three, if you count the geometric version. But I found two examples of, three examples. The geometric version is the one that doesn't use vector math. I prefer vector math. I think it's more useful and it's just easier to read most of the time. And so the first one I found was from a person that said, I make no guarantees to his correctness, and I don't remember how. He basically solved this a few years back, and he doesn't know how it works. And so that's unfortunate. Now, by comparison, I found another person here. Where is this guy? One of these. There it is. So this is awesome. Howling Software. Thank you so much for this, because we're going to be using your solution on the show. And it's already in Unity form, which feels like complete cheating. But because it felt like cheating, that's the reason I started trying to figure out what's missing here. So in his case, he remembers how it works. But he just fudges over getting the coefficients. He just shows, these are the way you calculate the coefficients. Solving it isn't too hard. I'll spare the details. And I agree, it's probably not too hard when you know how. And so let me explain what I got so far out of this and show where I got with the proof, and then we're going to actually use this to do our equation. So basically, what the solution is we are going to be pretending that we're expanding a sphere around the player in all directions. And there's a point where that sphere will intersect with as it grows over time. So the sphere is a product of time, right? And over time, it will grow to the point where it is the same distance to the final position as the equation for the movement of the ship, which to get to the final position. So this is a graph just showing two-dimensionally the distance of the ship, and this is a ship moving at an angle away from or towards, or is this away from or towards the player? It doesn't matter. It is moving at an angle, and that's the reason it creates this curve. This is actually kind of generated from the sinusoidal activity from it actually moving away while we're going. And so it's not moving in a linear fashion. It would only be moving in a linear fashion if it was moving on that plane that's the distance away from us, which is what we solved for. That's the simple case. That's the linear case. So so you basically solve for both these equations at the same time, and the intersection point is what you want. And so when you solve for both the equations at the same time, I'm going to show you how far I got. I did not finish this. This is not done. So basically, we have distance to target equals time to target times projectile velocity, and we have distance to target equals camera dot transfer dot position minus target dot position plus target velocity times time to target dot magnitude. Now, this is multivariable stuff, and what we're doing actually is it's actually single variable. Our variable is actually time to target, but we have two equivalencies. So we can say that this equals this. So we can do that here. So that's what we've done here. And then we need to solve it into a quadratic form. And so I started doing that. We divide both sides by projectile velocity. So we get time to target equals this whole thing divided by projectile velocity. And then we subtract time to target from both sides so that we get 0 equals our equation here. And this equation actually, in some way, supposedly, unless I'm doing something wrong already, which is entirely possible, translates into the quadratic form, which is ax squared plus bx equals, or minus c. And once we have it in that equation, we can then solve it using the quadratic formula, which he actually gives a fancier version of the quadratic formula. And he also says that in this particular special case, like, remember, quadratic formula gives you two answers usually. In this case, we don't care about the second answer. Remember, we did the last time we used the quadratic equation was to solve for ballistics. And the two answers represented the low angle and the high angle for hitting the target, which is actually useful in ballistics. In this case, the two versions is, if you have two answers, it means that the ship is traveling towards you. And so, as it's... I'm going to actually bring up my screen real quick. Forgive how I look. Just the face. So, if we're going this way, I should probably... let's do it this way so that you can see. So, we're here. The enemy is over here and heading towards us, right? And so it's going to like pass by us, right? So the two answers is, one is the one that would hit it like when it's here, and the other is the one that would hit it when it's already past us way over there. And so it's not really useful. So we just can throw away that extra thing. So I'm going to go back to our screen. And so he just throws away that extra result. He also uses a slightly different version of the quadratic equation. I haven't seen this one before, but it's evidently referred to as the alternate form, and I really like it. I think I'm going to have to figure out exactly where that comes from and how to derive it at some point, because that's cool. I like to know how things work as well as how to work things. Even though it looks like I just care about how to work things on this show, I actually really do care about how things work, and because when I know how things work, I can solve other things with the information. So I'm sorry I don't have the full solution here, but this is kind of in the direction of what's going on. So now we're just going to plug in his stuff and make it work. So after all that math talk, I'm going to actually keep this. We'll put that in the project folder somewhere. So I'm just going to steal this. This is a sweet calculation here. So, target lead position. Also, he solves for something that we didn't handle, which is if we're moving, what is the thing? So, VR is the relative velocity of the gun and the target. So we need to actually know our relative velocity because of how the ship is actually moving is based on our relative velocities, not just the ship velocity. So let's actually put this in as a function. So we're just going to paste this in. And it doesn't need to be protected. Let's just make it float. So what we need is the delta, in this case, represents... Hold on. Delta... Okay, so VR is the relative velocity. So delta is actually, I don't know why he used different terms here. So VR is the relative velocity of the gun and the target. Delta is the relative position of the gun and the target. And muzzle velocity is the muzzle velocity. So what we're going to do, and actually I think he just shows how to do it, but I'm going to just use it. So we want the relative velocity, so relative velocity. So we're going to add we're not actually going to do anything with it. We're going to add a rigid body this, just so that I can show you the solution with a rigid body. We're not going to move it to prove that it works, but we need to have it so that we have the velocity information. It's going to be 0 in all of our cases right now. But so relative velocity equals target dot velocity minus rigid body dot velocity. Is that right? Actually, let's just see what he did here. So target velocity minus gun dot velocity. Okay, perfect. That's exactly what we did. Delta is target position minus gun position. So we're doing delta. So this is vector 3 relative velocity. Vector 3. Oh wait, no, the delta is just the actual distance, right? No, it's not. Okay. Delta equals target dot position minus camera dot transform dot position. Yeah. I have to change we're paraphrasing his code a little bit here. So, and then finally we've got muzzle velocity is just the projectile velocity, so we can just pass that in. So we get these, and then we pass in, so we do aim ahead, not distance, time to target equals, we're just going to call it float time to target because we're probably going to just be using this portion. I'm just keeping this stuff up here for reference. So time to target equals aim ahead, and we grab the delta, the relative velocity, and the projectile velocity. So that gives us our time to target, and then our position equals target dot position plus target dot velocity times time to target. There it is. So since we have time to target now, we can do that, and I'm going to get rid of these two things, and hopefully this will just work. Maybe we'll get it right on the first try. So we're going to hit save. We're going to see if there's any compile errors. Looking good so far. And now we're going to see if this actually works. So we're going to hit play. And missing component exception. There's no rigid body attached to target lead position. Oh, we don't want the... Okay, so we need to get the player information out of here. So the reason we can't do this is because I was trying to get... I don't know why I was trying to get the... I don't want rigid body velocity. I actually want the player velocity. This script is attached to the little target lead indicator itself. So I'm going to just mark the camera as a player, or main camera. We'll just do that. Actually, I can just do camera.main. That's fine. So we'll just do camera.main.rigidbody.velocity. Save. So we hit play. We shouldn't get that missing component exception problem anymore. So now if I move this out so that it's moving away from us or something, and we fire. Looking good. Stay on target. Stay on target. You know, I am going to call that a win, considering the distance that we were engaging at. That was real right on. So let's go ahead and try it like what it moves forward to. I should probably have an up and down example too, but I'm not going to because I know that the up and down works. That's the easy part. So we're going to fire. Yeah, that's perfect. That's a beautiful thing. All right, so sorry I didn't have the full equation stuff for you guys. And as I said, I will come back with that. Also, I forgot to mention earlier. So we had some problems with the broadcasting last night. We might have problems with the broadcasting this morning as well. We do have local copies, and I will be re-uploading last night's episode and this one if necessary. So, but I'm really glad this actually worked out. So I'm going to go ahead and call that a wrap. So thank you very much for joining. If you have any questions, please email me pushypixels@pushypixels.com. You can also tweet me at Drakfire. That's Drakfyre. Thank you very much for joining us. And if you can, please donate. Put patreon.com/cookingwithunity. Really appreciate your support. People pay big bucks to go to college and learn this stuff, and this is a lot cheaper. I'm not saying it's necessarily as good as college, but it's pretty good. I've had some people say this better, but it depends on the college, I would imagine. So have a good one, and see you later.